Today I'd like to talk about vector fields, which are yet another type of function that we'll think of. Given a region R in the plane, or a region Q in three-dimensional space, what we're going to mean by a vector field is that it's a function that does this. For each point in your region, you get a vector back again. For example, I might have the vector field f, which will be a function of two-dimensional space. F evaluated at a point xy is the vector x plus yi plus x minus yj, and for various points you can evaluate this vector field at those points and get a specific vector back again. In general terms, we're going to say that vector field f has components m and n if you're in 2 dimensions. If you're in 3, you'll also have a p of x and y. We say that such a field is continuous at a point if m, n, and if you're in 3 dimensions, p, are continuous functions. Obviously, when you draw graphs of vector fields, you can't draw all of the vectors in because every point in the plane would be covered up by at least one of these arrows. So what you do is you draw selected points on the plane or in three-dimensional space. You put the initial point of the vector at the point you're talking about. Also, we usually draw vectors that have a common length to them. So, for example, you might have a vector field f of x and y, which would be y times I plus x times j. The magnitude of that is obviously radical of y squared plus x squared. If you wanted to look at places where that vector field took on constant values in magnitude, that would mean that radical y squared plus x squared would be c, x squared plus y squared would be c squared. You would be looking at circles of various radii, center at the origin. For this particular vector field, you can draw in a wide variety of points. For instance, the point 1, 0 would be the vector 0, 1. So at the point 1, 0, I'll put the initial point of my vector and I'll draw the rest of the vector in as indicated. When you interchange two radical 2's, you get two radical 2's back again. So if x and y were both radical 2, I'll put radical 2 over 2, that is. I'll put my initial point at that point. I'll draw in a vector with equal positive x and y components. At the point 0, 1, you'll get the vector 1, 0. So at this point, I'll draw in this vector, and so on and so forth. If I wanted to look at some other circles, I could look at circles of radius 2 and draw in the corresponding radii, and radius 3, and so on. One particularly interesting type of force field as a vector field are the inverse square fields. The vectors that we're going to look at point from the location that we are at towards the origin, and the magnitude of the vector values are inversely proportional to the distance squared. So doing the end minus start thing again, this says that f must be parallel to the negative of x comma y as a vector. A unit vector that points in the appropriate direction is negative x comma y divided by its length. So we want the vector to be a constant number divided by the distance squared multiplied by a vector of length 1 that points in the appropriate direction. After all the simplifying is done, the vector field will be the negative of a constant over the 3/2 power of x squared plus y squared multiplied by vector xy. If I want to look at all the places in the plane where this vector field takes on some particular constant magnitude, c, that would say that k over x squared plus y squared needs to equal c. X squared plus y squared would be the constant k over c, and we would be talking about circles again. To be more concrete about it, make the constant k equal to 1. The magnitude of f, as we know it's going to be, is 1 over x squared plus y squared, so that when I look at larger circles, I'll have arrows that point towards the origin, but when the circles get bigger, the length of the vectors will get smaller. So if one were to draw in some representative arrows, you would get this kind of picture. In the remainder of today's discussion, we're going to talk about some new words. Some of them look new and very odd to us, but are just based on ideas that we've had before. Others are less clear. So we're going to talk about conservative vector fields, which is a property that a given vector field may or may not possess. We're going to talk about potential functions, which are related to the conservative vector fields. And we're going to talk about curl, div, and gradient. We already know about the gradient. We don't know about the curl and the div yet. We say that a vector field is conservative if the vector field in question is actually the gradient of some ordinary scalar function. I'm going to use the letter u for the scalar function. Your textbook uses the lowercase or script f, and I think that would just lead to confusion because of the capital F. If you can find such a function, you call the u the potential function for the vector field. If you were in 2 dimensions and you had such a thing, the gradient of a scalar function is the partial of u with respect to x times vector I plus partial of u with respect to y times vector j. But on the other hand, we said that we were generically going to call 2-dimensional vector fields as m times I plus n times j. In order to get a conservative field, these two things, the m and the partial of u with respect to x, would have to be the same quantity, and these two things, the n and the partial of u with respect to y, would also have to be equal. Every field which is obtained from taking the gradient of a scalar, therefore, is automatically one of these conservative fields. So if I make up a potential function, u equals x squared y cubed, then f equals gradient of u will be 2x times y cubed I plus 3x squared y squared times j. This is automatically one of these conservative vector fields. On the other hand, if somebody just plopped a vector field down in front of you and asked you, is it conservative or not, it's going to turn out that there's a fairly easy way to decide. Really, this is a two-way argument. I'm going to suppose that f is conservative and come to a certain conclusion. to do the complete proof, you should start with the conclusion and convince yourself that f is conservative. But for now, we're just going to do half of it. So suppose f is conservative, then you could write f in this format, or in this one. As we said, m has to be the partial of u with respect to x, and n has to be the partial of u with respect to y. We're going to assume that m and n have partial derivatives themselves, and that those partial derivatives are continuous. If that's the case, partial of m with respect to y is the second partial of u, first with respect to x and then with respect to y. Partial of n with respect to x is the second partial of u, first with respect to y and then with respect to x. And you'll remember, if these partial derivatives are continuous, then this quantity and that quantity are the same. So, relying on that equality, that says that the partial of m with respect to y has to be the same thing as partial of n with respect to x if f is conservative and the functions have continuous derivatives. Then this must be true. It turns out that if this is true, then the function is conservative, but we don't know how to prove that yet. So for now, we'll just accept this tacitly. So if someone walked up to me and said, here's a vector field, f is x squared plus y squared I plus y squared minus x squared j, is that conservative or not? What I can do is I can look at m, the first component, which is x squared plus y squared. I can look at n, which is y squared minus x squared. Partial of m with respect to y is 2 times y. Partial of n with respect to x is negative 2x. Those are not always equal. Answer, no. There is no function u whose gradient will give you this f field. This is not a conservative field. Having discovered that, if someone went off and spent a lot of time and energy trying to find the potential function, they're just wasting their time. Here's a question. Is an inverse square vector field conservative? So we would have our field as a constant over x squared plus y squared to the 3/2 power times vector xy. As we've seen before, if you multiply the outside scalar through the components of the vector, you find out that m has to be that, and n has to be that. What we'll do is we'll calculate the partial derivatives involved and see if they're equal to each other. Partial of m with respect to y, after writing the quantity in this format, k times y is a constant in this context, so pull it out of the derivative. I've got something involving y raised to the negative 3/2 power. The derivative of that will be negative 3/2 times the negative 5/2 power of the quantity times the derivative of x squared plus y squared with respect to y, which turns out to be this quantity. So after simplifying, we get partial of m with respect to y is negative 3k, which is a constant, times xy times x squared plus y squared to the negative 5/2 power. On the other hand, if you look at the partial derivative of n with respect to x, write down what n is. In this context, x is the variable, so k times y is a constant. You can pull it out. Negative 3/2 times the negative 5/2 power of x squared plus y squared, but this time it's multiplied by the partial derivative with respect to x of x squared plus y squared. So this time, instead of having a 2y at the end, we have a 2x instead. The 2 and the bottom of the fraction cancel out. Negative 3 times k times x times y times x squared plus y squared to the negative 5/2 power. This is the same as the partial derivative of m with respect to y. This field is conservative. If you have an inverse square vector field, I guarantee you that it is conservative. That is to say, the field itself is the gradient of some scalar function. Now that we know that, we can ask the question, can you produce such a function? Write down what we know. We know now that there is a function u, so partial of u with respect to x is the first component of the vector field, and not only that, partial of u with respect to y is the second component. I'm going to write these as ordinary integrals. I probably ought to write partial x and partial y, but that's not what people do. It is true that this equation is valid. It is true that this equation is valid. I'm going to make a substitution here. I'm going to let p equals x squared plus y squared. In the context of this integral, x is the variable and y is a constant. So really, I should write partial of p with respect to x is 2x. I should write 1/2 curly dp equals x curly x, but people don't do that. They just use the d symbol anyway. X times dx is 1/2 dp, so I write that in. I've got my constant. I've already taken care of the x, and the number on the bottom is the 3/2 power of x squared plus y squared. After making these substitutions and pulling constants out front, all I have to do is integrate the negative 3/2 power of p with respect to p, which is easy. We could do that in Calculus 1. It turns out to be negative constant over square root of p, that is negative constant over radical x squared plus y squared. This is the negative of a constant divided by the distance from point that we're talking about to the origin. Now, there is one little detail that I've left out, though. What about the constant of integration? We were doing derivatives and integrals with respect to x, so I could take my computed potential function and add a constant to it. Constant in this case could mean an actual constant, or it could be a function that doesn't depend on the variable x. To be careful, I'll write down a function that might have y in it. If you look at partial of u with respect to y equals the second component of the field, if you do an exactly analogous situation, you'll find out that u is negative k over the distance plus something that's a constant with respect to variable y. It could depend on x. U has to look like this. Also, u has to look like this. The thing that you're adding on in this situation can't depend on y, and it can't depend on x in this one. The c and the d would have to be constant values. People usually take the constant values to be 0 so that the potential energy at infinity is 0. That turned out not to be all that difficult. What about three-dimensional space? We will call the components of our vector field m, n, and p. O looked too much like 0 to be comfortable with, so we'll use p instead. If you have a conservative field, the first component has to be the partial of the potential with respect to x. The second component has to be the partial of the potential with respect to y. And the third component has to be partial of u with respect to z. So if we have a conservative field, it certainly must be true that there is a function u so that these three facts are true. Now, in a way that's similar to what we did before, I want to look at relationships between m and n, but also I could look at m and p, and thirdly, I could look at n and p. The calculation is practically the same. For the relationship between m and n, m is partial of u with respect to x, n is partial of u with respect to y. In this one, differentiate with respect to y. In this one, differentiate with respect to x. Partial of m with respect to y must be this. Partial of n with respect to x must be that. If the functions are continuous, the mixed partials are equal. So partial of m with respect to y must equal partial of n with respect to x. This is what we had in the two variable case. Then compare m and p. M is partial of u with respect to x, and p is partial of u with respect to z. Take the first one and differentiate it with respect to z. Take the second one, differentiate it with respect to x. If all of the derivatives are continuous, this equals that, so that has to equal that. So this fact must be true. Having done that, I'll form a similar relationship between n and p, and it's the same exact logic as before. It turns out we have a third relation. Partial of n with respect to z must be partial of p with respect to y. If the force field, if the vector field is conservative, if it's got a potential function, then these three facts must be true. So this would give you a way to decide whether a field was conservative or not. There's a notation that we're going to adopt. It'll be convenient for us in several circumstances, one of which is it helps me remember these relationships that we were just speaking of. If I have a vector field, mi plus nj plus pk, we're going to define the quantity curl of f to be a cross product. It's the cross product of the derivative operator with the vector field that we're talking about. At first glance, what I just said doesn't even make any sense, but we'll see. How do you do cross products? I, j, and k across the top, and then the components of the first vector next. I'm thinking of derivatives here. Partial with respect to the first variable, partial with respect to the second, partial with respect to the third, and then the components of f, which are m, n, and p. Curl f is going to be a vector. This looks very bizarre. All we have to do is to remember this. When we do a determinant, if part of it is a differential operator and the other part's a function, you always write the differential operator first and the function second. By which I mean, after you've gone across the first row and split up into I, j, and k, when it comes time to do this first determinant, it's going to be the derivative with respect to y of p minus the derivative with respect to z of n minus partial of p with respect to x minus partial of m with respect to z, partial with respect to x of n minus partial with respect to y of m k. If you think back to what we did earlier, one of the things that has to be true if a vector field in 3 dimensions is supposed to be conservative is that partial of n with respect to x has to equal partial of m with respect to y, partial of n with respect to x minus partial of m with respect to y. If the original field were conservative, this would be 0. But what about the rest of it? Another thing that has to be true in order to have a conservative field is partial of p with respect to x has to equal partial of m with respect to z. If this were true, this component would be 0. And lastly, partial of p with respect to y has to equal partial of n with respect to z. If my field f were conservative, this would have to be 0. So if we go on and write the components out, define curl of f to be this, which is just the material on the previous page written out in component form. F being conservative means curl of f is 0 every place. If curl of f isn't 0 every place, then f is not conservative, and the del cross f notation makes it easy to remember all of these things. We already know about the gradient. We've just now learned at least the definition of the curl and one use for it. There's one other commonly occurring vector differential operator that we should know about. This is called the divergence. If I give you a vector field, f, which is mi plus nj plus pk, what I mean by the divergence of the vector field is often written as a dot product. This just means it's the partial of m with respect to x plus partial of n with respect to y plus partial of p with respect to z. The divergence of a vector field is a scalar field. Every point in space has a number to go with it. The gradient is a vector field. The curl is a vector field. I want to mention one other fact, and then since this is getting very lengthy, I'm going to call it quits for the day. If you give me a vector field, its curl may or may not be 0 every place. It depends on whether or not the vector field f is conservative or not. But as you might expect, there is a ton of identities that these operators obey. And one of them is this: assuming that the vector field has enough continuous derivatives to do all the calculations we want, then something very strange happens. The divergence of the curl of a vector field is identically equal to 0. Firstly, why is that true? I'm going to take the divergence of the curl of f, and we had already written out the components of the curl. To do the divergence, I have to take the partial derivative with respect to x of this component plus the partial derivative with respect to y of that component plus the partial derivative of z of this component. I'm going to use the subscript notation so I don't have to write so much. This would give me the second partial of p first with respect to y, then with respect to x, minus the second partial of n first with respect to z, and then with respect to x, and so on and so forth. Assuming the derivatives are continuous, this one and that one are equal to each other, so they cancel out. I have this one and that one being equal to each other. They'll cancel out too, and that minus that also cancels out. So as long as these derivatives are continuous, which is going to be almost always for us, you're guaranteed that the div of the curl of f is identically equal to 0. This should sort of remind you of something. We had equations earlier on in the course, in third semester calculus, where we wrote a vector as the sum of two other vectors, one of which was easy to get rid of by doing a dot product or a cross product, say. This is very much in that spirit, so we'll be making use of this identity a little bit later. Since this has gone on for quite a while, I'm going to stop it here today. In our next meeting, we'll talk about line integrals.